My name is Martin Gillar. I work at Waters Corporation and I will be talking about RNA purification. In this presentation, I will discuss the ion pair reverse phase chromatography method, its resolution, and a choice of ion pairing systems, show the application for a guide RNA, and then describe the purification of oligonucleotides under overloading conditions. Finally, I will mention what the max peak high performance surfaces technology is and what is it good for. Ion pair reverse phase chromatography is a version of reverse phase chromatography where ion pairing reagents are added into the mobile phase, typically charged amines, to enable both retention and better selectivity of separation for oligonucleotides. The separation is performed at elevated pH and temperature, at which the silica columns, silica sorbents, would not last very long. That's why we use high pH stable hybrid silica sorbents. And we pack them into both analytical and prep scale columns. I should also mention that the sorbent is batch tested and only the best batches are approved for separation of oligonucleotides. There are multiple alkyl amines that one can choose as an ion pairing agents. They could be roughly separated into polar, hydrophobic, or very hydrophobic, or as we like to also call them, between weak and strong alkyl amines. And the rationale for choosing of the polarity of alkyl amines was listed and discussed in the paper that is listed on the upper right side. Basically, when one uses more hydrophobic alkyl amines, the elution of oligonucleotides must be or is realized with stronger organic solvent, higher acetonitrile concentration. And that in turn leads to suppression of hydrophobic interaction that is also participating in the separation of oligonucleotides. So we prefer hydrophobic alkyl amines as an ion pairing agents because we can resolve adequately longer oligonucleotides, and also the separation becomes less sequence dependent. Here I show an example of analytical scale separation of long oligonucleotides. I have these pairs of 39 and 40, 69 and 70, and so on, up to, let's say, 99 and 100 mer. This is the separation that is performed with the hydrophobic alkyl amine system. It's a 100 millimolar hexyl ammonium acetate. And we are using analytical scale column 2.1 by 150 millimeter long column. So the separation shows that we can achieve this n-1 pair resolution. Baseline separation is basically achieved until 70 mer, and then the selectivity declines, but we can still resolve even the 100 mer from the 99 mer. Even though this is an analytical scale separation, we can also scale it up into a prep scale, as I will show on the next slide. This example shows a separation of 100 nucleotide long sgRNA. It's a crude RNA synthesis, so the main peak here, which is labeled with the sign 9% yield, that's the main product. All of the smaller peaks eluting in front of it are so-called n-x failed products of synthesis. If you look at the relative ratio of those peaks, and when I integrate the main peak, it comes up to about 9% yield. You can also see that these multiple peaks eluting in front of the main peak, if you count them, you would have arrived to about 98 peaks count, suggesting that we indeed have a resolution of all those impurity products. This is achieved with 4.6 by 100 millimeter long column. In this case, I'm using 300 angstrom pore size column, which is more suitable for the separation of longer oligonucleotides. And the separation is achieved with 100 millimolar hexyl ammonium acetate buffer. This slide basically shows the same scenario, same separation as on previous slide, that 1 nanomole injection black chromatogram is the same as you just saw, except now I am injecting more of the material on the same analytical scale column. Red chromatogram is 5 nanomole, blue chromatogram is 10 nanomole, and 25 nanomole is green chromatogram. As you can see, I also get larger amount of UV signal. Peaks are getting bigger, somewhat fatter, but the resolution is still preserved. If you start collecting close to the peak top of the main peak and choose the proper fraction collection window, you will still be able to purify the let's say 95 plus purity of your 100 mer oligonucleotides. So we recommend about 1 to max 2 mg of material to be loaded on the analytical scale column. If you need to purify more material, we offer 10 millimeter or up to 50 millimeter prep columns. So ultimately you can purify in a single injection something like 100 milligrams or low hundreds on the prep scale column. When performing the fraction collection under heavily overloaded conditions, you will get, for example, the chromatogram shown here, which is an example of 25 mer phosphorothioate oligonucleotide. We loaded 10 milligram on analytical scale column, and indeed that peak is no longer a sharp peak. It's a 10 minutes, so it's a 15 minutes wide zone, and it is not entirely obvious when to start collecting your target fraction. So we collected fractions every 30 seconds and resorted to reanalyzing them very quickly after the purification, and then decided which fractions are gonna be pooled together. For your information, remember the number. Fraction 71 shown here is in front of the peak top. Peak top is fraction 74. What I didn't mention was that in that purification we split the output from the column and 1% was directly to mass spectrometry detector, which enabled us to monitor the mass of the target product labeled here as N, and you can see that this is indeed a white peak. N-1 and 2 and 3 are neatly sandwiched on a front of that peak. They are now sharp and partially resolved peaks. So based on the mass spectrometry, it becomes very easy to decide when to start and finish collecting the desirable fraction. In case that you don't have a mass spectrometry detection, you can do what we did here. That means we had a method to quickly reanalyze the quality of collected fractions. Fraction 71 contains mostly impurities. Fraction 73 contains still noticeable amount of N-1, 2, and 3 impurities. And beginning of fraction 74, which is at the very top of that zone, the fraction was acceptable purity, 95 plus. And up to fraction 91, this was the case. The fraction contained mostly our 25 mer. Beyond that, we started to see so-called N plus X products. So we stopped the fraction collection or pooled only fractions up to fraction 91. At this point, I would like to switch gears and describe a phenomenon that some of you may have observed, and it is non-specific adsorption. This could be illustrated by two chromatograms that I show here. Upper right chromatogram is an analysis out of the box, fresh new column, that is stainless steel column, and it is an injection of an oligonucleotide, and presumably you know very well this oligonucleotide, and you would immediately see that something is not right. The early eluting peaks are not present, and sometimes peaks tail a bit, and every next injection, second, third, and fourth, are looking differently. These peaks reappear in chromatogram as you are used to. So we observe this phenomenon in our lab as well. It is due to non-specific adsorption. This has been described in literature. And the explanation for this phenomenon is that there is some non-specific adsorption of oligonucleotides to the column itself. Now we have investigated this and created a technology that corrects this problem. It is called MaxPeak Premier High Performance Surfaces technology. And when we make columns with this technology, you can take this column fresh out of the box and inject the first sample, and it will look like the chromatogram at the bottom. So all peaks will be there and the non-specific adsorption is minimized. This non-specific adsorption was described in literature. I list the papers on this slide. And basically, when the columns are made out of metals, either stainless steel or titanium, all of these metal materials have a surface coated with metal oxides. And because the metal oxides have amphoteric nature, they could, under acidic conditions, obtain positive charge, and oligonucleotides as anions like to get adsorbed on those positive surfaces. This effect is less noticeable in neutral conditions and goes away at pH, let's say, above 9. So now we understand that the adsorption, non-specific adsorption to metal surfaces, is most noticeable for ionic molecules, acidic molecules like oligonucleotides, and happen most noticeable at low ionic strength and at low pH. We have studied this phenomenon and we described our results in the 2 papers listed in blue at the bottom. Based on our research, we now have a solution that is called MaxPeak High Performance Surfaces, and it is basically a modification, chemical modification of metal surfaces that block the possible interactions of anions with the metal oxide surfaces. This technology is described in the paper listed below, and we have this technology applied to both columns, column body, column frets, as well as HPLC or UPLC systems, so-called premier version of those, which have the metallic parts that come to contact with sample also modified with this hybrid inorganic organic silica technology. In conclusion, ion pair reverse phase chromatography is a very efficient method for purification of oligonucleotides. You could purify 1 milligram up to 100 milligram of materials with a analytical to prep scale columns. I also showed you that if you are bold enough, you could overload the column more than people would usually dare, without loss of separation and purity. The only problem is to choose the proper fraction collection window. Finally, I mentioned MaxPeak HPS technology, and I didn't mention at this point that it has a direct impact into prep mode as well, because if there is a non-specific adsorption, it could also show up as a carryover, and with the high performance surfaces, this carryover is minimized. So at this point, I thank you for your attention.